Some general comments. About entropy and chaos. It is quite possible at this point that the student may have a good grasp of the material that has been covered, and yet we have only a vague understanding of the significance of entropy. The question, what is entropy, is frequently raised by a student. Reach the implication that no one really knows. This section has been included in an attempt to give insight into the qualitative and philosophical aspect of concept of is about give insight into the qualitative and philosophical aspect of the concept of entropy. And to illustrate the broad application of entropy to many different disciplines. Illustrate the broad application of energy to many different disciplines. First, we recall that the concept of entropy arises from the first law of thermodynamics, arise from the first law of thermodynamics, and the concept of entropy from the second law of thermodynamics. Actually, it is just as difficult to answer the question what is energy as it is to answer the question what is entropy. However, since we regularly use the term energy and are able to relate this term to phenomena that we observe every day, the word energy has a definite meaning to us and thus serves as an effective vehicle for thought and communication. The word entropy could be served in the same capacity if when we observe a highly irreversible process such as cooling coffee by placing an ice cube in it with a surely increased entropy. We would soon be familiar with the word entropy as we are with the word energy. In many cases, when we speak about higher efficiency, we are actually speaking about accomplishing a given objective with a smaller total increase in entropy. A second point to be made regarding entropy is that in statistical thermodynamics, the property entropy is defined in terms of probability. The entropy is in statistical thermodynamics the property entropy is defined in terms of probability. In terms of although this topic will not be examined in detail in this book, a few brief remarks regarding entropy and probability may prove helpful. From this point of view, the net increase in entropy that occurs during an irreversible process can be associated with a change of state from a less probable can be associated with a change of state from a less probable state to a more probable state. For instance, to use a previous example, one is more likely to find gas on both sides of the parchment membrane than to find a gas on one side and a vacuum on the other side. Thus, when the membrane departure example gas, vacuum, and memory. When the membrane repurchases, the direction of the process is from a less probable state to a more probable state, and associated with this process is an increase in entropy. Similarly, the more probable state is that a cup of coffee will be at the same temperature as its surrounding than at a high temperature. Therefore, as the coffee cools, as a result of transfer from heat to surrounding, there is a change from a less probable to a more probable state, and associated with this is an increase in entropy. To tie entropy a little closer to physics and to the level of disclosed disorder or chaos, let us consider a very simple system. Properties like U and S for a substance, U and S for a substance at a given state are averaged over many particles on the molecular level, so they do not all exist in the detailed quantum state. There are a number of different configurations possible for a given state that constitute an uncertainty or chaos in the system. The number of possible configurations, W, is called the thermodynamics probability of possible W is called thermodynamics probability. And each of these is equally possible. This is used to define the entropy as S K L N W, where K is the Boltzmann constant and it is from this definition that S is connected to the uncertainty or chaos. The larger the number of possible configurations is, the larger S. For a given system, we would have to evaluate all possible quantum states for kinetic energy, rotational energy, vibrational energy, and so forth to find equilibrium distribution and W. V in a given system for a given system we would have to evaluate all the possible quantum states for kinetic energy. Rotational energy, vibrational energy. And so forth to find the equilibrium distribution and W. So forth to find the equilibrium distribution and W as thermodynamics properties, thermodynamics probability. Without going into those details, which is the subject of statistical thermodynamics, a very simple example is used to illustrate the principle. Assume we have four identical objects that can only possess one kind of energy, namely potential energy associated with the elevation in a tall building, as this picture. This picture shows a tall building. Let from object have a combined 2 units of energy. Therefore any object, 4 objects have a combined 2 units. Floor height times mass times gravitation, mgh as we know. How can this system be configured? We can have one object on the second floor and the remaining 3 on the ground, giving a total 2 units of energy. We could also have 2 objects on the first floor and 2 on the ground floor, again with a total of 2 energy units. These two configurations are equally possible, and we could therefore see the system 50% of the time into one configuration and 50% of the time in the other. We have some positive values of S. Same value of. Now let us add 2 energy units by heat transfer. That is done by giving the object some energy that they share. Now the total energy is 4 units, and we can see that the system in the following configuration as A, B, C, D, E, as shown in this table. Number of objects A, B, one, two, three, 4. 0, 1, 2, 3, and 4. At point A, we have 3 objects in the First flow and can be obtained the values here. Now we have 5 different configurations, each equally possible. So we will observe the system 20% of the time in each one, and we now have a larger value of x. So probability for each is W thermodynamic probabilities that we can have a different choose. On the other hand, if we have increased the energy by 2 times through work, it acts differently. Work is associated with the motion of a boundary, so now we pull in the building to make it higher and stretch in the twice as tall. That is, the first flow has 2 energy units per object and so forth as compared with the original state. This means that we simply doubled the energy per object in the original configuration without altering the number of configurations. With state at W equals to, in effect, S is not changing, as shown in the picture. This example illustrates the profound difference between adding energy as a heat transfer change S versus adding energy through a work term leaving S unchanged. In the first situation, we move a number of particles from lower energy levels to higher energy levels, thus changing the distribution and increasing the chaos. The second situation, we do not move to a particle between energy states, but we change the energy level of a given state, thus preserving the order and chaos. Summary and the key concepts and formulas are the next section.